The finite element method FEM is a way of obtaining approximate or numerical solutions to differential equations. Broadly speaking, the FEM is used to reduce differential equations to a system of equations which can be more easily solved. There are two usual ways to derive this system of equation using Galerkin's weight residual method or variational method together with Rayleigh's scheme. Both of these approaches are discussed below, but former being more general of two is one which is followed in the most of this text. The Galerkin method is described where variational approach is also described. The weight residual method, the FEM using Galerkin method is more specifically called Galerkin finite element method, GFEM. Before discussing GFEM, which is done in the next it is worthwhile discussing Galerkin method from which it derives. In fact, many of the important concepts of FEM are touched upon. Galerkin's method is what one might use to obtain solution to differential equations if one didn't have computers. It was only with the development of computers in 1950s that Galerkin method generalized to Galerkin FEM. Galerkin method is one of the number of numerical techniques known as weight residual methods. These various weight residual methods are often as effective as each other, but it is Galerkin method which leads naturally into the finite element. The two other most commonly encountered weight residual methods are collocation method and method of least square. These are special cases most general retro-Galerkin method. Collocation least square Galerkin method will be illustrated here through the following one-dimensional example problems solve linear ordinary equations. So d square u by dx square minus u is equal to minus x, where u of 0 is equal to 0, u of 1 is equal to, this is the boundary conditions. In exact solution, u of x is equal to x minus sin of x divided by sin of hl. By assuming from to u usually a polynomial. For example, take a trial function u of x is equal to a plus bx plus cx square. This trial function has three unknowns, two of which immediately obtained from the boundary conditions, leading to trial functions which automatically satisfies the boundary conditions. U of x is equal to b into x minus x square. It now remains to be determined b. The collocation method. The most direct method is to satisfy the differential equation at some point in the interval x 0 to 1. This is the collocation method. Which point one chooses it is arbitrary, but it makes sense to choose midpoint, which usually yields best results in which each substituting into setting x is equal to 1 by 2. One finds b is equal to 2 by 9. It's the approximate solution. So u of x is equal to 2 by 9 x minus x square. Slightly different results will be obtained by choosing to enforce the differential equation at different points. More accuracy can be achieved by choosing higher order polynomials. For example, one could begin with a cubic and so have a trial function which satisfies BCs. So bx plus cx square minus b plus c into x cube. With two unknowns, one needs two equations. For example, enforcing the equation Euclid-spaced points x is equal to 1 by 3 and x is equal to 2 by 3 leads to system of equations. 62b plus 2c is equal to 959b plus 29c is equal to 9, and solving this leads to approximate solutions. U of x is equal to 1 by 560 81x plus 9x square minus 90x cube. The term 1 and 2 approximate solutions are grabbed, the latter being virtually indistinguishable from the exact solution at this scale. Using the methods to describe here, one would expect one term solution within perhaps 10 to 20% of an exact solution. Even more accurate solutions can be obtained by increasing the order of polynomial and solving systems with ever great number of equations. The collection method solutions. The term 1 and term 2. Term 2 is an exact one. The method of least square. Alternative solution procedure wherein a differential equation is multiplied crossed by some weight functions omega of x and complete equation is integrated over the domain. So integral 0 to 1 d square u by dx square minus u plus x into omega of x into dx is equal to 0. You can choose trial functions which satisfy the boundary conditions. So the integral 0 to 1 d square u by dx square minus u plus x omega of x into dx is equal to integral 0 to 1 bx square plus 1 minus b into x minus 2b omega of x into dx is equal to 0. The term inside the square bracket is the residual r and it is which one wants to drive 0. The idea here is if the integral is 0 for arbitrary weight function omega, then residual should be 0. There is one unknown and the question is now what function omega of x does. Again choice is here somewhat arbitrary. In the least square method one choose omega of x is equal to dou r by dou b leading to cubic integral. So 47 by 10 b minus 13 by 12 is equal to 0 where b is equal to 60 by 282. So b is equal to 2 by 9. Note the prime difference between the collocation method and least square method. In former, the differential equation is satisfied at one or more particular points. The differential equation is forced to 0 in some average way, determined by weight functions over the complete domain. So the equation is u of x is equal to a1 x plus a2 x square minus a1 plus a2 into x cube. This time with two unknown coefficients, one requires two equations which are obtained by choosing two different weight functions. Omega 1 of x is equal to dou r by dou a1 is equal to minus 7x plus x3. Omega of 2 of x is equal to dou r by dou a2 is equal to 2 minus 6x minus x square plus x3 x cube, leading to two integral equations which can be evaluated to obtain 1436 by 105, 2783 by 420, 2783 by 420, 449 by 105. In sub matrix, then vector a1 a2, then displacement, then force vectors equal to 32 by 15, 21 by 10, from which we can calculate the value of a1 is equal to 0.1485, a2 is equal to 0.0154. Gives approximate solution which close to the exact solution to the problem. The reason why least square method works is as follows. If integral is 0 for the complete set of solution, omega 1 is equal to 1, omega 2 is equal to x, omega 3 is equal to x square, then the residual will be initially 0. As one takes higher order polynomial trial function, the weight functions omega 1 is equal to dou r by dou a1 contain higher order terms in x and more times from the complete set of solutions. The solution is obtained with ever increasing accuracy. The collocation method as weight residual method. Now collocation method, it can be seen that this is also weight residual method with weights omega of x is equal to delta x minus x dash. So where delta x minus x dash is equal to 1x is equal to x dash and 0 otherwise, direct delta function. So I is equal to 0 to 1. So d square u by dx square minus u plus x into delta into x minus 1 by 2 dx is equal to d square u by dx square minus u of plus x is equal to 1 by 2 is equal to whole 0. Symmetry of least square method. The coefficient matrix of least square system is symmetric. This is always desirable, particularly for large system of equations, since special rapid equation solver algorithms are available for symmetric coefficient matrices. The least squares coefficient matrix is always symmetric provided the differential equation is linear. This can be shown. So L of u into f of x. So u is equal to sum of a1 x dash leads to, provided L is a linear operator. So L a y x power I is equal to summation of a I L and power is equal to f of x with the weight functions.